pleased to have as our next speaker Heinz Robota. Get your we're pleased to have Dr. Heinz Robota from Centrolium, who will be talking to us on regeneration.
Thank you, Cal. I'd like to thank Cal for giving me the opportunity to share some of this work with you. My intent here is, perhaps a little facetiously, is not to enlighten you, but to befuddle you, because that's sort of where we are with respect to the kinds of observations that we're making in connection with a simple catalyst. In this case, it's a completely unpromoted cobalt on aluminum catalyst, and what happens to it when we put it through some regeneration cycles. So I'd like to thank some of my collaborators here, Shelley Goodman, who's in the audience, Ronnie Young, who was important in doing a lot of the actual manipulations of the catalyst in the laboratory, James Engman, who's also here in the audience, and Vladimir Gruber, who's with us, and he'll actually be talking to you next about another topic. What I'd like to do is just talk to you a little bit about boosting cobalt on alumina activity. There's been a lot of talk about that already, and so I'm going to go through that very quickly because most of you will have heard just about everything that I would say about it. Talk to you a little bit about our regeneration process so you understand what manipulations we're doing in the laboratory and why, and then actually show you what the impact of regenerating these catalysts is on the activity. Talk a little bit about the extent of reduction of cobalt metal, because I think that that's important, and I'm not convinced that it's always used in the same way. So I want you to understand exactly how we're using it and why I think it's important to be consistent in the way one talks about this phenomenon. I'll talk a little bit about the methane time profile, because that has some impact on how we try to understand what it is that we're observing. I'll throw out some plausibility considerations, but that's it. I'm looking for you in the audience to take some of this and run with it, and hopefully help us understand that better, and then take you through what we think the conclusion is. As has already been said, one of the key things to getting an active cobalt catalyst is that you have to reduce it to metal. That's the name of the game, the active number of metal sites. And so the way in which the catalyst is typically made, impregnate, dry, calcine, and reduce. Nothing magic to here, and that's exactly the way that we made the catalysts that we're using in this study. In order to reach about 20% cobalt, which is the loading on these catalysts, we had to go through this cycle 3 times. Now, these catalysts don't reduce readily. It's partly dependent on the loading of cobalt, but with respect to catalysts that are around 20% cobalt only, you end up with extensive reduction that are quoted in the literature of somewhere 25% to 35%. That's a pretty normal value. It's attributed to the formation of some kind of stabilized thing. And unfortunately, I don't have a good chemical picture of what that stabilized thing is. And I have yet to see a good chemical picture of what that stabilized thing is. Because if we understand what that chemical entity is, then perhaps we have ways of attacking it, breaking down that stabilization, doing something along those lines. But this stabilization is routinely invoked in these cases. And we're talking about stabilizing oxide particles that are tens of nanometers in extent. So how this works is a little bit difficult to understand. Now, practical catalysts, which I'm not going to be talking about here, I'm talking about an impractical catalyst. They're promoted, right? We've already seen platinum, palladium, rhodium, ruthenium, rhenium. All those are encountered quite frequently, and as a consequence of using those, you can get much higher extensive reduction so that you can get that active cobalt area that you're seeking. This is a cartoon schematic of the way in which the Centrolium regeneration process is envisioned to operate, and it actually does operate this way. We've been running it this way now in a demonstration plant for several months. We have a slurry bubble column reactor.
Your head's feedback.
Yeah, I know. So if I move over here, I guess I can't manipulate the tank over here.
Yeah, but if you stand right back there.
Stand right here. I'm pinned to the corner. I'm not used to being pinned to the corner. Slurry bubble column reactor. You take some of the slurry out through the top through a settler. This basically allows the solid to settle. You have an overflow that is largely liquid. It contains a little bit of solid that you'll use to slurry up what comes out of your regenerator. you have to take the wax off of this catalyst, and so we have a dewaxing step. Then from the dewaxing, we go to really an oxidation step to where you burn off some of the spectator carbon material, some of the residual hydrocarbon, but also some of the carbon, in fact, hopefully all of the carbon that's involved in deactivating your catalyst. Go through another reduction, re-slurry it, send it back into the reactor. And this would be envisioned then to go on basically the whole time that these plants are in operation. The way we do this in the laboratory is that we start off with a relatively large charge, meaning somewhere in the neighborhood of maybe 80 cc's of catalyst in a 1 liter reactor. The fresh catalyst, again, we start off by reducing it. And if you'd like to see more details of, just some of the chemical steps that we're using in these regenerations, this has just come out as a patent, so you're free to go ahead and take a look at that. Do a reduction in pure hydrogen, gas harvey space velocity about 6,350 C, again, pretty typical number that people are using. Hold that for 8 hours, put this into the reactor. In our case, what we did was in the first go-around, we ran the reactor for about 1,000 hours, and then we took the catalyst out, went through the dewaxing steps, went through an oxidation step, burn off all the carbon, re-reduced it, put it back into the reactor. This time we ran it for about 500 hours, went through the cycle again, and in total we subjected this catalyst to 3 rounds of regeneration. So it's going through the reactor. It's actually had multiple times through the reactor operating, regenerating. This is what we observed. This is the activity reduced to some kinetic rate factor so that everything is normalized. I should also point out that over the course of these hundreds of hours of operation, we've tried to hold the conversion level of the catalyst constant. So that means that while it deactivates, the parameter that we're adjusting in order to keep the conversion roughly at about 50% is the gas hourly space velocity. So we're holding temperature fixed, we're holding pressure fixed, and we're changing the rate at which we bring the feed in so that we can keep the conversion level relatively constant. What you can see is that when we start off with the initial charge of the catalyst, and I'm only showing data out to 500 hours here, on this scale it has an activity of about 0.5, and it's relatively constant over time. We send it through one regeneration, and you'll notice that the activity now is substantially higher, decays a little bit over time, and then stabilizes. Put it through a second regeneration, gets a little higher, third regeneration. Whether or not this is really higher or not, considering all the manipulations that we're doing, is questionable, but I think that you'll agree that going from here to here, there's been quite a bit of change in the properties of the catalyst. The other thing that I think that you'll see is that if we look at the extensive reduction, is that they're also changing. When we start off with the initial catalyst, the way we go about measuring the extent of reduction is by taking the reduced powder in a glove box and basically putting it on a balance. And we allow it to oxidize and look at the weight that's gained, and we make sure that it's fully reoxidized by it at some point once it's stable to air. Take it, put it in a furnace at some reasonable temperature in air, and then reweigh it to see how much weight it gains. And so that way we can measure the extent of reduction with really quite high precision. What you can see is initially, extent of reduction is about 27%. Go through one regeneration, jumps up to about 36%, and then the last two, they're closer. 46, 49%. Now, if you just look at the extent of reduction, the apparent extent of reduction is only differing by a factor of 2. But if you look at the activity, if you look at what one might call the intrinsic activity, it'd be very close to 0 hours, maybe 20 hours on screen, it looks like a factor of 6. Even if you look out here, you can see that there are changes in activity on the order of factor of 2.5 to 3. Well, one of the things that I think is important to understand, again, and this has been talked about, is what are the phases that are present and how does this influence our picture of the catalyst. Fresh oxide, it's all cobalt 304. This reduction was done in an in situ X-ray diffraction instrument that allows us to treat the catalyst in the instrument itself and never have to expose it to air. So we can look at it right as it's being reduced. What we find is that all traces of the cobalt 304 are gone, and we have predominantly now cobalt monoxide left, and we can see that there is a little bit of reduced metal present in a crystalline form that allows us to see it. Now, I'm going to jump the gun a little bit, but basically if you're going from cobalt 304 down to cobalt metal, if you have an extent of reduction of 25%, which I'm going to round 28% to 25%, that corresponds perfectly with taking cobalt 304 exclusively to cobalt monoxide. So we shouldn't have any metal present. Yet we can see that we have metal present. So that means that there's got to be some residual cobalt 304 in this thing that we're not able to see anymore. It's become amorphous. We're no longer able to keep track of all of the phases of this catalyst. So exactly where the cobalt is and what it's doing chemically has started to get a little bit confusing. So here's the question. Can more metallic cobalt particles explain these differences? And that's what I'm going to try to convince you, is that if you actually don't just rely on this simple notion of extent of reduction, but come up with some strategy for actually counting the number of metal particles, this is actually quite understandable. Here's the equation that we use for measuring extent of reduction. And basically, like I said, it looks at the fraction of the oxygen that was associated with cobalt in the cobalt 304 spinel and how much of that disappears when you do a reduction. Nothing more. There's no microscopic model, there's no chemistry associated with that. To go to metal, you basically have to lose, on our catalyst, you have to lose 7.2% of its mass. You see how much mass you lose, or in fact how much mass you regain. You normalize that, that's your extent of reduction. One of the problems we have here, you see, is that we actually have only two equations and we have three unknowns. But now let's look at our diffraction. Even though I told you already that there's probably still some cobalt 304 there, let's ignore that, okay? What happens if we just set cobalt 304 fraction to 0? Now we've got two equations, two unknowns, it's easily solvable. And what you can see is, like I said, if you start off with a 25% extent of reduction and you assume that there's no cobalt 304 left, you de facto can have no metallic cobalt. So we know that we've got a little, we've got catalytic activity, we can see it in the diffraction. What happens now when our extent of reduction goes from 25% to somewhere around 50%? Well, it looks like we can go from, say, maybe a mass fraction of metal that's, 0.05 here up to 0.4. That's an 8-fold increase. That's on the same order of the increase that we actually observe. So I think it's really important to not just talk about extent of reduction. Somehow or another, we have to be more careful about figuring out how much metal do we really have. And like I said, we made the assumption that cobalt 304 is absent, even though we know in the fresh catalyst at least that there's probably still some left. It's not an easy chemical problem to solve. Let's talk a little bit now about what happens to the methane selectivity when we regenerate these things. You can see initially it starts off around 6%, climbs over the 1,000 hours of operation to somewhere around 11%. That's a pretty substantial change. Interestingly enough, when we regenerate it, starts out at about the same place, climbs up 500 hours to about the same level, but now it levels off. It doesn't seem to want to keep going up. Regenerate it again, now we're down below 6%. Levels off at an earlier time. What you will see is that this transient period here appears to be very similar for all these cases. Regenerate it again, methane selectivity drops a little bit more, still get that kink at about the same time, drops off even more. Well, what's happening here? One of the simple things that you could invoke is, well, the first time you reduce this catalyst, you reduce all the big particles, you make big particles of metal. And then as you subsequently regenerate it for some unknown chemical reason, you actually begin to produce more smaller particles that are harder to reduce initially. Does that mean that smaller particles make less methane? I don't think there's any evidence for that. What about where within the actual spherical, microparticles the cobalt is reduced? Is it possible that those larger things are being reduced in the larger pores first? And as we subsequently recycle, we're reducing more and more of the cobalt that goes deeper and deeper into the pores. There's been a fair number of papers recently using, for example, mesoporous materials looking at the impact of porosity and the reducibility of cobalt. Does that mean that particles in deeper and narrower pores make less methane? That's actually contrary to what other studies have suggested and shown, so that's not a good explanation that we like either. Does cyclic regeneration change the surface morphology? You know, that's an easy thing to throw out. How would I know? How would I tell? What's going on? Don't have an answer. One of the other things we see is that as we get more activity, we have this transient deactivation that always runs out to about 250 hours. And that's where the methane selectivity has its peak as well, 250 to 300 hours. What's responsible for this transient activity here? Is it, some have suggested that what we're having here is reoxidation of small particles. And that once you reoxidize all those small particles, then it settles down and things become stable again. Well, that gets back to saying that small particles make less methane. I don't understand. Is this pore filling now? Because out here, we reduce particles that were in the mesopores, larger pore area, and as we get deeper and deeper into the pore structure of the particles, that gets filled up, it slows down, and we're actually seeing some diffusional effects. That's a possibility, but again, how does that influence the methane selectivity? I can't reconcile those two observations. So, I've already talked about this. Here's a schematic of a big, long, fat molecule, C60, C80, those things fold back on themselves. Are we seeing that we have contact stabilization in these pores that somehow we're breaking up? I can't explain all these things. What about hydrogen spillover in the actual initial reactions, right? Well, why hydrogen spills over from cobalt metal, can't it spill over as readily as it could from a promoter? I don't understand that. Is contact required? Do I have to have my promoter in contact with my oxide particle? There's been some evidence showing that you can actually get atomic declaration from the group of Johnson-Matthey on some of these things with promoters, because that's what's required to actually get these reduced. Well, if so, why do some reduce and others don't? What about the rest of the cobalt? It looks like even under the best of circumstances here, in an unpromoted catalyst, we only get about 30% of the cobalt as metal. What that says to me is that there's still a huge untapped potential, which was talked about earlier today in this catalyst right here, that if we could find a way to actually reduce these things completely, that we could unleash and make these catalysts much more attractive in the marketplace. Does something happen when we go through the cyclic reoxidation of cobalt 304 to cobalt monoxide back to cobalt 304 in our regenerations that then makes some of this cobalt monoxide easier to reduce? Right? Since we don't really know how the support is making this cobalt monoxide reduction resistant, perhaps these expansions and contractions have something to do with it. How about the water that's produced during the synthesis? Does it somehow intrude? I realize this is heresy, but does it somehow intrude on this cobalt aluminum linkage? In that the water that you produce intimately during Fischer-Tropsch synthesis then ease up the reduction of some of these particles? Don't have an answer. So I think that everyone would agree that in our hands, repetitive cycles of FT operation and regeneration lead to subsequently higher performance from the same catalyst. The extent of reduction increases with each cycle, but it seems to level off at about 30% of the cobalt being converted to metal. Transient behavior, it increases, right? We get those deactivation things. It suggests that possibly cobalt in deeper pores is being reduced, but the methane selectivity doesn't quite go along with that. And support-related stabilization does appear quite strong, but we don't have a good microscopic chemical view of what that is. And so maybe some of you can help us get to that view. So with that, I'd like to address any questions that you might have. Thank you.
Back there? Yeah. Bye-bye.
I don't think I have a question for you. How do you measure the extent of reduction of the use of catalyst?
No, the problem with the used catalyst is that it's completely covered with wax. And so, you know, de-waxing it is not a trivial activity. And in fact, in order to get all the residual carbon off, you really have to do an oxidation, so that interferes with it. We are, at this point, actually working on a way to try to get a handle on that. But we're probably months away from even figuring out whether it's going to work or not. But that is one of the things that we're trying to do. Yes. Yes. It continued, well, yeah, it certainly will continue for beyond 500 because we ran that catalyst for 1,000 hours. And it just stayed flat for 1,000 hours. But it's very low activity.
Professor?
The Young Utrecht University, you mentioned in bypassing that you applied for a patent in this methodology to regenerate the catalyst.
Yes.
In the 1970s, Gulf had a number of patents that they refer to as reduction, oxidation, reduction, ROR.
Yes.
And I was wondering what is now the delta between the Gulf patents and your approach?
Well, I didn't go into that in detail. I really just sort of jumped over that. If you look at the ROR patents themselves, first of all, largely they refer either to a fresh catalyst or a catalyst that has been used sparingly. Also, they typically observe factors of 2 or less increase in activity. And so we're seeing factors of 6 increase in activity for these catalysts. The commercial patent for the regeneration system, now that's a completely different thing. But the detailed chemistry, one of the things that I didn't point to on here was, I think the largest activity increase I could find was for some catalysts that they had made using cobalt carbonyls as a precursor. And if you want to point me to other ones, that would be very helpful. Okay, that would be very helpful. But in our hands, just doing ROR on these catalysts does not produce this large of an increase in activity.
Well, Heinz, I wish we could continue the discussion, but we have to move on because we have a tight schedule. We thank you very much. We're pleased now to hear from Dr. Vladimir Gruber, who will talk to us about some deactivation problems that occur in slurry reactors.
Good morning. Thank you very much for introduction, and I also would like to say thank you to my colleague from Central Corporation for their contribution in this work. First of all, here is outline of my talk. I would like to explain which carbon we are talking about, how to quantify, how to quantify this carbon, then where is this carbon located, if this carbon has intimate contact with solid and deactivate it. Controlling commercial fission torque reactor will be a slurry bubble column. During operation, both demonstration scale and pilot scale, we observed slow long-term deactivation. And this work focuses on the cause of this deactivation, specifically on the raw carbon. the effect of water produced and its impact on activation during Fischer-Tropsch synthesis dominate discussion of Fischer-Tropsch catalytic activation. Here is very incomplete list of work which devoted to this topic. But other causes of deactivation should be anticipated also. It's very well known that CO decomposed on such metals like cobalt, nickel, iron, producing very active alpha carbon. But this carbon easily reacts with hydrogen, produces Fischer-Tropsch product. But at the same time, alpha carbon can transform other form of carbon. It was shown for nickel catalyst, and here slide was taken from work of Kelvin Liu. It was done for nickel. Different form of carbon were classified using the reactivity with hydrogen. So it was done for nickel, but a few work was done for nickel. In our previous work, we found that during slurry operation in continuous stirred tank reactors, under hydrogen depleting condition, we observed different transformation of other form of carbon except alpha. It's cobalt carbide, a polymeric or graphitic carbon, which was unremovable by hydrogen and treatment at 350 C. In result, activity was sharply reduced and selectivity decreased also. So the question is, if this carbon produced on cobalt catalyst in real conditions, commercial conditions, in slurry above power. Fischer-Tropsch synthesis was carried out in two sequential SBC reactors using Centronic proprietary cobalt aluminum catalyst. Commercial conditions were applied in both columns. Sample of H catalyst last compact were collected from both reactors at different upstream times. The carbon-related phases from H catalyst were analyzed using method-tolerant thermogravimetric analyzer coupled with Pfeiffer mass spectrometer. Here is the method which we use to quantify amount of carbon. First of all, we need to remove wax from the catalyst. Usually, catalyst contains about 30% of spectacular wax. To do it, we treated catalyst in hydrogen at temperature 350 C during 2 hours. During the ramp of temperature to 350, we observed very significant loss of weight, which started at 200 C peaked at 250 and completed during the whole at 350. At the same time, very intensive peaks of methane were produced. So we removed most part of we removed wax from the catalyst, then cooling down and combusting the catalyst and in air, you can detect the every carbon which cannot remove at this stage. During the combustion, we absorb CO2 peaks in a range of temperature between 200 and 450. Catalysts contain reference amount calcium carbonate, which produced reference. Compare with peaks, you can identify the amount of carbon, hydrogen resistant carbon. Hydrogen chemosorption was measured at 100 C using automatic ASP 2010 system. Before chemosorption, both catalysts used and fresh were treated by hydrogen in situ at temperature 350 for 8 hours. The crystalline component of the catalyst were identified using untoned power cell coupled with power refractometer. We used copper pair alpha radiation. ESRT present were obtained at 100 C in flow of dry nitrogen. At this temperature, wax was melting and interference from strong diffraction features of crystalline wax were eliminated. Here is typical XRD pattern of loose catalyst. Blue spectrum is a spectrum of original catalyst. Pink is spectrum of alumina, which was supposed to be catalyst. Spectra were normalized using the strongest alumina band at 67 degrees, and as a result of subtraction, you got yellow spectrum which contain a reflection only of cobalt phases. No, only cobalt metallic crystalline phases were detected. There didn't absorb no spinal production, as well as cobalt carbide in this case. So there is no oxidation by water during 3400 of RAM and CDS, tone and industrial conditions. Here the result of carbon evaluation. You see the hydrogen treatment works very effective at removing paraffinic wax at low temperature, 250 C, but some carbon resists hydrogen even at 350 C. And this carbon for each reactor increases and from stream time increases. was the nature of the scatter of carbon. We did the same experiment with other research did with on nickel. So we did thermograph soft reaction with hydrogen, and we got the several forms of carbon present in this catalyst. This peak at 400 was equivalent of classification with polymery carbon or beta carbon, and maybe also some other carbon which more likely versus present in our catalyst. The measured amount, the content and measured cobalt dispersion, 6%, carbon residual mass of 1% has 3 times the number of atoms as number of cobalt contained surface atoms. To find out if there is intimate contact with cobalt, we do hydrogen associated measurement. You can see that fresh catalyst has surface cobalt surface area approximately 2 times larger than used catalyst. But in this case, we did hydrogen treatment at 350. So maybe this treatment altered the surface area. So we did other way. We remove part of this carbon by combusting by air at centrolium, using centrolium proprietary regeneration structure. Results, we got family of catalysts which contain different amounts of carbon. And here the result. Fraction of the carbon resistant to hydrogen affects the surface phase of decreasing its active surface area. We observed that approximately 20 atoms of residual carbon need per lot one surface metallic element. The loss of fissile activity was proportional to amount of this carbon for each reactor. And here's conclusion. During Fischer's crop synthesis in slightly bubble column under commercial operating conditions, hydrogen-resistant carbon slowly accumulates, deactivating cobalt aluminum catalyst. Based on analysis of similar carbon on nickel, it appears most likely to be polymeric of that carbon. A fraction of the polymeric carbon interacts with metallic cobalt, considerably decreasing its active surface area. Loss of catalyst productivity is proportional to the amount of the hydrogen-resistant carbon remaining. Therefore, a slow secondary production of this carbon is one of the causes for cobalt catalyst activation.
We have time for a couple of questions. Hans?
I wonder whether this hydrogenation resistant carbon is formed via coking. Via coking when during your procedure, when treating it with hydrogen. then you will, with a large molecule, there will be also coking, and then you get some coke on the surface. And it could be some sort of coke here, which is now being thought that a sort of carbon in the real Fischer-Tropsch synthesis.
What procedure do you
The regeneration procedure. He's asking if during the regeneration procedure you would decompose some of the waxy hydrocarbons to coke and then to carbon.
No, because most of wax produce methane, absorb the production of methane. And also the amount of this carbon was proportional. The amount of time during operations CBS. We have the same procedure, but for different categories.
Any other questions? We want to thank our speaker.